All right.
It's like the fairy dust food world.
It's like the fairy dust what?
That's the food world.
So what do these look like, you guys?
Galaxies.
They do look like galaxies. And we're going to spend time talking about galaxies. What galaxy is our sun in? The Milky Way galaxy, exactly. So one of the things about galaxies up there is that they often interact. Do they look like these two galaxies are dancing? I think so. What's at the center of our galaxy?
The black hole.
The black hole, exactly. There's a black hole here and a black hole there. Does it look black? Mm-mm. It is. It is black. There's an object in there. That black hole actually is, I hate to say it, but it is taking in matter. Okay, matter is falling into the black hole. And as matter gets ready to fall into the black hole, it kind of creates this sort of energy, and that's the energy that you see is the brightness of a center of a galaxy. So that stuff is outside the black hole, but the black hole is causing things to heat up and make that glow like that.
Where's the black hole going?
Where's the black hole going? It's just there.
Or is it just there?
Yeah. But that's an interesting point. These guys are doing a dance. Does it look like they might kind of merge and kind of run into each other? Yeah.
Is that what the Milky Way's going to do with that?
Yes, that is what the Milky Way is going to do with Andromeda. So we can make this MW for Milky Way, AND for Andromeda, and there you have our kind of situation. Okay, so it happens.
10 billion years from now, I think is the estimation.
Okay, that could be 10 billion years for the merger to begin between Milky Way. That's neat.
And then billions of more for it to go on.
I can buy that. What do you think is causing this? First letter G.
Gravity.
Yes, I would say gravity. Yeah, and that's one of the things we're going to talk about. But the thing about understanding like galaxies and stars and stuff like that is you need to understand gravity, but we're going to kind of look at gravity on a smaller everyday scale. Like, why does my pencil fall? Because of gravity. Yes?
Is this kind of, is this explaining Einstein's concept of gravitational pull?
No.
Well, Einstein, though, did talk about the fabric of space. Basically, kind of what we're walking in, space and time are actually one. So,
Yeah,
Yeah.
two things merging together.
yeah, this is definitely kind of, gravity is an Einstein thing.
There was something last year, the year before, that was proven to be right.
Gravity waves.
Yes, yes, gravity waves in ripples in the fabric of space and time. So, but before Einstein, of course, you guys might recognize this is Sir Isaac Newton, due to an apple fell on his head. I kind of chased that down one time. Did that really happen? I think so. But anyway, so Isaac Newton was a great mathematician, and he did a lot of great things. Now, the cool thing about what was a photo of those two face-on galaxies doing a slow dance, going to merge, okay? The cool thing about, I think I already said, on the big scale, gravity operates the same way as it does on a small scale. I guess that's all I was trying to say. Okay. So in order to kind of make sense of what Newton said, we need to talk about some terms, some everyday terms you already know. How fast are you going? What's your speed? Okay. You could say, and we'll go metric, so meters instead of miles. You could say I'm going so many meters per S is seconds, okay? So you instead of miles per hour, meters per second. That's how fast you're going. That's your speed. Now, it's a subtle thing between speed and velocity, and some of you may know this. But the difference between speed and velocity is speed says how fast you're going, and velocity says how fast you're going and in what direction. That's velocity. So velocity has a directional component to it in addition to how fast you're going. So a lot of times then we can use arrows, and this is kind of this is my like little kind of physics lecture just a little bit. We could say this person is going 10 meters per second, and what direction would that be? 10 meters per second. What do you think? If that's a map, what direction is that?
Right.
East, right. Either way, we're going to go east. Exactly. I'm going to double the length of that arrow and try to. So that'd be 20 meters per second, and then what direction? South, yeah. So those are velocities. And it really is kind of fun in physics because really if you make sure you're careful with your scale of your arrows, you can kind of add them together, these vector quantities sometimes, and kind of get what we call the resultant vector. But yeah. Now one more thing, acceleration. So our cars have an accelerator, right? So we're used to kicking on the accelerator and going faster. Okay, that's a type of acceleration. Acceleration means that you're changing your speed and or you're changing your direction. So check this out. These are all examples of acceleration. Do you want a little baggie for your cookies? Do you want a little baggie for your cookies? No. Dayton? Baggies. Baggies, ladies. Okay, so this is all acceleration. So this person, is he changing his direction? No. Is he changing his speed? Yes. He's increasing his speed. Now notice, what do we call it? It starts with the letter D. What do we call it when we hit our brake? Deceleration, that's right. Deceleration in physics terms or whatever is a type of acceleration because it's negative acceleration, you know. You're changing your speed. If you change your speed, you're accelerating. All right. So this person, is he changing his speed? No. Is he changing his direction? Yeah. And sometimes that's a hard one to kind of see, but it sounds like you guys got it. If I were to draw an arrow in the center of their car, his car or her car, that arrow is going like this to kind of down the middle to show, okay, oops. And that arrow keeps changing, okay? So even though they kept the speed constant, if you're changing the direction you're going in, you are accelerating. Okay, now, here we go. I'm going to go ahead and put what's this? Well, it's been different things, but now it's the sun, okay? So this is the sun, okay? And what shape do the planets orbit the sun in? An ellipse, very good. Okay, so it might look kind of straight over here, but because kind of the flat part of an ellipse. But am I changing my direction? Mm-hmm. So as planets, but it could be, and it's, well, we kind of talked about this. When does it go fastest? When it's close to the sun or when it's far from the sun? When it's closest to the sun, that's right. So we do have a little bit of change in kind of our speed too, but the fact that we're changing the shape of our path, circular, means that we're accelerating. The planets are accelerating. Okay? All right, and I guess I do have one more here. See that stop sign? So again, you don't hit the accelerator, you hit the brake. Everyone's like, get those mixed up. That's not a good thing. Okay? So you hit your brake, and of course this vehicle's going, not changing direction, but it's changing the speed. And if you're decelerating, it's a negative acceleration. Okay? So if you're slowing down. Now, the important thing about this is in all these cases where I'm going to show you, and actually Newton, this is one of his laws, if you're accelerating, okay, whether you're hitting the gas pedal or hitting the brake, or heck, if you're just going in a circle, if you are accelerating, then there's some force making that acceleration occur. Some force. It might not be an obvious force. It might be very obvious. But some force always has to be in play to make something accelerate. So... all right, so Newton's 3 laws, and I have a little note here. It must be out of order. So yeah, I see you flipping pages here. Newton's 3 laws. Doesn't, I mean, you see something like this, you're like, that little, is that like got people in it? Does that look like the top of a rocket with a payload could be people? I just am amazed at space travel, you know? Like, oh my gosh. But the blackness kind of looks like it's in outer space, right? And I don't know if you've watched many science fiction movies, but something in outer space, have you heard this? Like if If you get it to go in an outer space, it's just going to go forever. Okay, because there's no gravity, no friction. It's just going to go forever. There was like I don't know what mission it was on. Maybe it was to try to help the Hubble Space Telescope or International Space Station, something. And I think it was a woman. She was outside the safety of the vehicle, and she was working, and she actually, there was like a screwdriver or something slipped. I know, you're like, oh. So basically, it's one of these things. If it wasn't tethered or whatever, it's just gonna go.
Does it go pretty quick? Or is it
Well,
just kind of
that's
float?
that's the cool thing about once they basically there's a force imparted by her accidentally, okay? But once she got it going, it's gonna go. Then there's no more force applied, and so it's just gonna go at that constant rate forever. I know. Trapped.
It's weird how it has enough energy to keep going like that, just by one, you said just by her
Yeah.
doing it?
Yeah, but the thing here is like, if we didn't have friction or gravity or anything, all the stuff here would just go. Yeah, because it's other forces that slow things down. I agree, though. It's interesting. Sometimes students will say, well, like, what if gravity, like, what if it fell to the moon, got caught up in the moon's gravity, and that could be, and kind of fell to the. It's possible.
Like, what if
It's
it
gonna
just
keep
gets
going
floated?
until it hits something.
Yeah, something has
Yeah.
to occur for it to stop.
Yeah, hit something or some other force acts on it, yeah. That's Newton's first law. Yep, it's gonna go at a constant velocity unless some other force makes it move or stop okay, that's his first law. His second law looks like this. And remember I said, if you observe an acceleration, so A here is acceleration, okay. If you observe an acceleration, there must have been some force acting upon it, and that's all it is. Force is equal to, what's the M stand for? Mass, yes. M stands for mass. So force applied is equal to, and this seems backwards to me, mass times acceleration. I kind of think of it as you observe an acceleration, that's how I think of it. You observe acceleration, and there must have been some force to cause that acceleration. Bless you. And you can kind of see how its mass is related to the acceleration you observe and the force you apply. So that was his other thing. So one of the reasons we're kind of talking about this in this class is I said that you guys told me that the planets orbit the sun in an ellipse, and that actually is accelerating, whether it's the whole kind of perihelion or aphelion thing. It's accelerating because of the shape of its motion. So it's accelerating due to the pull of gravity. All right. This last one, Newton's third law, and I kind of used to say we have 3 kids, and I guess it was more growing up. I just have one brother, and it's like the law of reaction. Every action deserves an opposite and equal reaction. So it's like, yeah, you hit her, she's going to hit you, that sort of thing. Okay. So the example here is showing you a rocket that's taking off. Okay. Basically, that's one thing about future space travel is instead of this chemical sort of reaction we have of basically using some sort of explosive hydrazine or whatever to burn it to go up, we're going to have to come up with some other sort of way to propel us. Okay, but anyway, this is a chemical reaction that is causing a force this way, which results in an equal force this way, and it makes the rocket go up. So basically you have, what I meant to say is you have a force this way and a force that way. So if this is my rocket, okay, I have a force of the chemical going like that, and it actually results in an equal and opposite force going up like that. That's how I think of it. Okay. And you see how I've kind of drawn arrows? A lot of times forces aren't visible, but we can kind of draw arrows to kind of show the tug and the push and the pull of forces. And the length of the arrow kind of says how strong the force is, and the direction is the direction of it. So it may not be obvious, but, well, it's obvious, like if I drop in this, unlike my cookies, is not fragile. Okay, so if I drop this, okay, it falls, right? Now, it may not be obvious, but if I were to clock it here, okay, it's going a certain speed. If I were to clock it here, it's going even faster. And clock it here, it's going even faster. Okay, it actually picks up speed as it falls. Of course, picking up speed is called acceleration. Okay, so we know here on Earth that, and you might imagine that how fast it's going to go actually is a function of two things. It's a function, well, no, it's just a function of one thing. I almost caught myself doing that. How fast it's going to go actually is just a function of the gravitational pull of the object it's falling to. Okay? It's not a function of the pen. It's one of the things I'm hoping that you guys will get, and I can't remember what slide it's on. I think it's coming up on this slide. Is if I were to take two objects, see if I find something else that's not breakable. Okay, well, that's pretty. This is expensive. That pen goes with this. I'm trying to find two things. There's an aerodynamic issue too. Okay. Well, this is a pretty good example. There's aerodynamics of these two. I'll pass them around. I wonder if we could do an experiment. That's okay. I'll get that in just a minute. Okay. So these, to me, this one feels a little heavier. Pass them around. So this one feels a little heavier. Now, it's a myth that because it's heavier, it's going to actually fall faster. It all falls, actually, for every second it falls, for every second it falls, it's going to fall 10 meters per second faster. Okay, let's see if I can do that. Regardless of the weight. So we might do this a few times. Let's see. Not bad. Do a little higher. Yeah. See? I don't know if you caught it. But the one is heavier. Yeah, they're like right on. And one of the things that I mentioned aerodynamics. If you go somewhere where there's no atmosphere, the aerodynamics doesn't play a part. Like for instance, if I were to have a scale in here, and I'm just guessing, I'm kind of liking these for kind of similar masses. Now, if I drop these, okay, they're similar masses. Which one do you think is going to drop first? Hit the ground first. I think it's the eraser too. Let's see. Yeah. I mentioned aerodynamics. Did you see this plate kind of go like this? Yeah. And if there was no air, they would hit the ground at the same place. So, actually, and I'll kind of post this video. I'm kind of surprised I don't have it in my notes. But one of the many things that the folks on the moon did was go up and they took a feather for a falcon feather, quite appropriate, and a hammer. Okay, obviously different masses. The hammer's heavier, and definitely different aerodynamics. The feather would just float down here, right? Okay, but on the moon, the atmosphere is very thin. So basically, they dropped them at the same time and they hit the ground at the same time. I know, isn't that cool? Yep. So this whole acceleration thing, what this, this kind of reminds me, David Letterman used to go up on and throw things off of his building just because it'd be funny, I know. Watermelons and you name it. So can you see where after 1 second, regardless of what you drop, after 1 second, it's going 10 meters per second. You allow it to fall another second, so 1 plus 1 is a total of 2, and now it's falling at a speed, again, aerodynamics, not in play, of 20 meters per second. What if you let it go for t is equal to 3 seconds? How fast would it be going?
30 meters per second?
Yep. 30 meters per second. It's just going to keep picking up speed. So now there's this thing while we're talking about aerodynamics. Based upon kind of the aerodynamics, the mass, and kind of the surface area, there's this thing called terminal velocity. here on Earth, and actually things kind of, they accelerate to a point, and they then end up going any faster. It's also a great movie. So, okay. So that's that whole thing. What's that?
Reminds me of those Boy Scouts did those derby cars, and they had to weigh a certain amount. but
Derby
they-
cars, yeah.
And they wanted to race them to get fit in, but they're not really going faster. It's just the aerodynamic of it.
Right. Yes. Yep. It's just kind of, it's how they've made their derby car to basically flow with the wind instead of, yeah. And maybe some wheel things, I don't know, friction or, you know. But this actually goes to that. They made sure that the derby cars weighed the same.
Yeah.
Yes.
I didn't understand that.
Yeah.
Like that.
And that actually has to do with this, I think, a little bit. Now, depending upon weight, you can have, let me put this all up here. You can have two objects going the same speed. Oh, I got this. Okay. Here's my two objects. Well, let's see. This is supposed to be my truck. I know it doesn't look like a truck, maybe. Okay. Going down the road at 30 miles per hour. Okay. And this is my bicycle. Okay. Going down the road at 30 miles per hour. Okay. So they're both going the same speed. Okay. Obviously, M1 is greater than M2, right? By a lot. So if they're going, the fact that they're moving gives them a certain amount of momentum. Anything that's moving has momentum. Momentum is kind of an easy thing. We just take the mass times the velocity. The symbol for momentum, I think, is P. But anyway, so we'll call it P. So can you see where the momentum of the truck is significantly greater than the momentum of the bicycle? Yeah. So I'm not sure if that, I have to think about the derby car thing. So which one would you rather be hit by, the truck or the bike? The bike. Neither. Okay. But yeah.
Kind of where I'm at right now.
What's that?
So that's kind of where I'm at right now.
Oh, sorry, that was not a good.
It's fine.
Oh, goodness. Okay. So, if something changes its momentum, then it has either changed its mass or its velocity. Okay, remember velocity is speed and direction. Okay. Now, if something, so say, I hate to keep doing this to you, Nicole, but say the truck goes ahead and hits a wall, okay, a brick wall. Okay, it goes from 30 miles per hour to 0. Okay, so it changes its velocity. Now we're going to look at conservation laws, and that energy, that momentum it had to be conserved. It has to be transferred somewhere. So where is it transferred to? Everything inside. Upon impact, it's transferred to the wall. Yeah. Yep. Okay. So one thing about it is we talk about forces. I mentioned forces sometimes can be obvious, like if you're pushing something. Sometimes forces are not so obvious, kind of invisible. But oftentimes a good example of two forces, like if I was to kind of try to make this go that way, why did it slow down? Maybe two things. Why does it stop? Because Newton's first law said it's going to go forever. What's that? I think so.
Completely flat surface, there's nothing to give it more acceleration.
The weight, it can't get any more acceleration. But Newton says, what force is acting upon to stop it? What? The momentum?
What's it start with?
No. Oh, yeah. I probably F.
Friction.
Friction.
No,
Yeah,
I
yeah,
think we went
exactly. Friction. Friction's one of those forces. Mm-hmm. Yep, and I think you've mentioned smooth. The smoother I get this, the less friction there is, right? So I could take these two, I could do this side down, and I could do this side down, I could do the smooth side down. Sorry. So, this is smooth, okay, this is rough. Which one's gonna go farther?
Yes.
The smooth one. Let's see. Oh. They got about similar.
Does it have to do with the weight of the balloon since it's heavy?
Yeah, the weight does make a difference because it's at the force downwards. Well, there goes that experiment. I think you get the idea.
Yeah.
Yeah. But there, in all of that little bit, I mean, there's a force this way, there's a force this way, and actually, kind of like you said, the weight, that's the force this way. So
Like, I would honestly say the one that has the rough part pointed down because it's like almost softer in a sense.
Yeah, I think maybe
Slicker.
less friction, it does seem like it might be less slick, or more slick. Yeah, it's interesting. Sorry. All right, I think I have one more thing here. Okay, one more thing. So this all just goes back to anytime you see acceleration of the planets is they change the direction they're moving. Okay, if it goes straight line, no acceleration. Circle, acceleration. Isn't this true that like when they build like a curve, like for cars to drive on, they go ahead and they bank it, and you're supposed to kind of accelerate into it? That's all there's on. So the fact that after 1 second, how fast was something falling?
10 meters a second.
10 meters per second. After 2 seconds, how fast was it falling? About 20. 3 seconds, you told me 30. The fact that it keeps picking up speed means that there's some force acting on it, and that's the force of gravity. And so I have kind of a slide coming up to kind of show you what that little equation is. All right, mass versus weight. Now this is a tough one for me. I'll go ahead and give you a heads up. Okay, you guys would probably buy the whole atom thing, that all matter is made up of atoms. Okay, atoms are great. And so how many atoms there are kind of in an object is its mass. It's like the quantity of atoms is the way I think of it. That's the mass. That's kind of, mass is most fundamental. Now weight actually then is a function of gravity. Okay? So weight is a function of gravity. Weight goes like this. Okay? The reason I'm doing that is because weight is a force towards the center of the object that's creating the gravitational pull. So that is weight. Mass is just mass. Okay? But we use them interchangeably all the time, which is fine. Cool. But even though we've used them interchangeably, there is this little formula, W is equal to M times G. Okay, W stands for weight. M stands for mass. So weight is equal to mass. And what is G? Gravity. In fact, we're going to go, it's the acceleration due to gravity. I think that's what I'm going to do. Okay. I think this is right. What did I tell you? What was that in, well, I'll just put it right here. Acceleration due to gravity on Earth is about 10 meters per second for every second it falls. So actually 10 meters per second, which is 10 meters per second squared. That's what your G term is here. So what do you think? We go to the moon. If you were to compare the mass of the Earth and the mass of the moon, what would you say about the mass of the moon? Does the moon have more mass or less mass? Yeah, the moon's moon is significantly smaller than the Earth. It's got less atoms. It's less massive. Yep. And you're probably fine with, and there's a formula coming up, but the smaller the mass, the less the pull of gravity. So the acceleration, you know, the guy I told you a little bit ago, the astronaut held up a falcon feather and a hammer, and they both hit the ground at the same time. You know, different aerodynamics, different masses. There was acceleration, okay, and it was constant. Okay, the moon does have gravity, but it's about the 1/6 of the Earth. okay? So instead of being, we said 10 meters per second squared, it's gonna be more like, let's see, 1/6? Help me out, what's 1/6 of 10? Point, point, 0.67, 3, 2, 1, about 12%. Okay, I think something like that. So you're gonna weigh less, you're gonna have the same mass on the moon, but you're gonna weigh less on the moon. So let's kind of finish up with this thought. This is how far we get. What's your next thought? Thank you. Good, okay, that's good. Okay, so here we have a guy in an elevator, okay? I don't know why you'd want to weigh yourself in an elevator, but that's what he's doing. He's got the same mass for all 4 of these scenarios. I know, scenario A, B, C, and D. So he's weighing himself in an elevator. Have you ever noticed this in an elevator? When do you feel the, whoa? Is it like when you first take off, when you've been in there for a while, or when you stop? Actually,
When you stop.
when you stop, exactly. When you stop, you're like, but have you ever, when you take off too?
Yeah. A little bit, yeah.
So both, when you take off, when that's accelerating, and when you stop, that's also accelerating, okay? So this right here, this first one, is where he's at the smooth part of his elevator ride, okay? This says the elevator is going up, but the elevator is moving at a constant velocity, okay? This is the smooth part, and that's the most accurate weight, okay? If we were to take an elevator trip, and they've talked about creating kind of like an elevator sort of situation where you can go to the edge of the Earth's atmosphere. Have you heard about that? Okay.
Yes, I think it's going to be 22,000 miles long to get up to the Clark Belt.
But if you were to take an elevator, see, Jay knows. If you were to take an elevator up, once you got, there'd be that jolt when you went from 0 to, oh my gosh, what if you went to like 100 miles per hour or
There would
something?
definitely have to be a gradual acceleration.
It's gradual acceleration. But once you're at 100 miles per hour, you're fine, okay? And then you have to kind of gradually decelerate. Yeah, at that constant velocity, there's no extra force on you. I
Is that
know.
like an airplane? Like when an airplane
Yes,
takes off, they
that's
kind
an
of go
excellent example of an
really fast,
airplane.
And then you don't really feel it. Not that I've been in one, 'cause
That's right. Airplanes are the same way. Once you get going, you're like, I don't care how fast it's going because I have the same trajectory as the airplane. Yeah, very good. So that's that one. This one actually is showing you when the elevator is taking off. So B is actually kind of the initial whoa. Okay, what happened to his weight? Did it increase or decrease? It increased a little bit. Very good. This one right here is where he is actually going down, and he's accelerating down. He's not constantly, he's accelerating down. What's his weight there?
Less.
A little bit less, yeah. And I kind of think of it as kind of the thing he's standing on is accelerating down, so I kind of think of that. This last one, this is what you're laughing at?
Yeah.
This last one, someone cuts the cable. They do that all the time in these superhuman movies, and somebody comes and saves him. So somebody, I'm sure, came and saved him. Okay. And we're going to talk Wednesday about this idea of free falling, okay? But basically the scale he's trying to stand on to create the weight, okay, is falling and he's falling, and so what happened to his weight?
He's weightless.
He's weightless. Yeah. So, yes.
Wednesday, if we aren't able to make it to the review, will you give us the review sheet in class?
Oh, I got the review sheet for you now. So we're going to pick up here on Wednesday.